The Sun is the star at the center of the solar system. It is a massive, nearly perfect sphere of hot plasma, heated to incandescence by nuclear fusion reactions in its core, radiating the energy from its surface mainly as visible light and infrared radiation with 10% at ultraviolet energies. It is by far the most important source of energy for life on Earth. The Sun has been an object of veneration in many cultures. It has been a central subject for astronomical research since antiquity. The Sun orbits the galactic center at a distance of 24,000 to 28,000 light-years. Its distance from Earth defines the astronomical unit, which is about 1.496 times 108 kilometers or about 8 light-minutes. Its diameter is about 1,391,400 kilometers, 864,600 miles, 109 times that of Earth. The Sun's mass is about 330,000 times that of Earth, making up about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, approximately 73%. The rest is mostly helium, approximately 25%, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star G to V, informally called a yellow dwarf, though its light is actually white. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. Every second, the Sun's core fuses about 600 billion kilogram of hydrogen into helium and converts 4 billion kilograms of matter into energy. About 4 to 7 billion years from now, when hydrogen fusion in the Sun's core diminishes to the point where the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature, which will cause its outer layers to expand, eventually transforming the Sun into a red giant. After the red giant phase, models suggest the Sun will shed its outer layers and become a dense type of cooling star, a white dwarf, and no longer produce energy by fusion, but will still glow and give off heat from its previous fusion for perhaps trillions of years. After that, it is theorized to become a super-dense black dwarf, giving off negligible energy. The English word sun developed from Old English sun. Cognates appear in other Germanic languages, including West Frisian Sinn, Dutch Zon, Low German Sun, Standard German Son, Bavarian Sunna, Old Norse Sunna, and Gothic Sunna. All these words stem from Proto-Germanic *sunnen. This is ultimately related to the word for sun in other branches of the Indo-European language family, though in most cases a nominative stem with an L is found, rather than the genitive stem in N, as for example in Latin sol, Ancient Greek lambda iota omicron sigma helias, Welsh hall and Chexlunce, as well as with *L greater than our Sanskrit svar and Persian xvr. Indeed, the L stem survived in Proto-Germanic as well, as *Swelen, which gave rise to Gothic Saul alongside Sunna and Old Norse prosaic Sol alongside poetic Sunna, and through it the words for sun in the modern Scandinavian languages, Swedish and Danish sol, Icelandic sol, etc. The principal adjectives for the sun in English are sunny for sunlight and, in technical contexts, solar, from Latin sol. From the Greek helios comes the rare adjective heliac, helic. In English, the Greek and Latin words occur in poetry as personifications of the sun. Helios, helix, and sol, while in science fiction sol may be used to distinguish the sun from other stars. The term sol with a lowercase s is used by planetary astronomers for the duration of a solar day on another planet such as Mars. The astronomical symbol for the sun is a circle with a central dot. It is used for such units as m solar mass, or solar radius, and L solar luminosity. The scientific study of the sun is called heliology. The Sun is a G-type main sequence star that makes up about 99.86% of the mass of the solar system. It has an absolute magnitude of plus 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. 2728. It is more massive than 95% of the stars within 7pc23 Li. The Sun is a population I, or heavy element-rich star. Its formation approximately 4.6 billion years ago may have been triggered by shock waves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, relative to the abundances of these elements in so-called population II, heavy element-poor stars. The heavy elements could most plausibly have been produced by endothermic nuclear reactions during a supernova, or by transmutation through neutron absorption within a massive second-generation star. The Sun is by far the brightest object in the Earth's sky, with an apparent magnitude of 26.74. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of 1.46. One astronomical unit about 150 million kilometers, 93 million miles, is defined as the mean distance between the centers of the Sun and the Earth. The instantaneous distance varies by about plus or minus 2.5 million kilometers, 1.6 million miles, as Earth moves from perihelion around the 3rd of January to aphelion around the 4th of July. At its average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 20 seconds, while light from the closest points of the Sun and Earth takes about 2 seconds less. The energy of this sunlight supports almost all life on Earth by photosynthesis and drives Earth's climate and weather. The Sun does not have a definite boundary, but its density decreases exponentially with increasing height above the photosphere. For the purpose of measurement, the Sun's radius is considered to be the distance from its center to the edge of the photosphere, the apparent visible surface of the Sun. The roundness of the Sun is the relative difference between its radius at its equator, rec, and at its pole, RPOL, called the oblateness, delta equals rec RPOL RPOL. The value is difficult to measure. Atmospheric distortion means the measurement must be done on satellites. The value is very small, meaning very precise technique is needed. The oblateness was once proposed to be sufficient to explain the perihelion precession of Mercury, but Einstein proposed that general relativity could explain the precession using a spherical Sun. When high-precision measurements of the oblateness became available via the Solar Dynamics Observatory and the Picard satellite, the measured value was even smaller than expected, 8.2 x 10^6, or 8 parts per million. These measurements determine the Sun to be the natural object closest to a perfect sphere ever observed. The oblateness value remains constant independent of solar radiation changes. The tidal effect of the planets is weak and does not significantly affect the shape of the Sun. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport and the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. Viewed from Earth as it orbits the Sun, the apparent rotational period of the Sun at its equator is about 28 days. Viewed from a vantage point above its North Pole, the Sun rotates counterclockwise around its axis of spin. A survey of solar analogs suggests the early Sun was rotating up to 10 times faster than it does today. This would have made the surface much more active, with greater X-ray and UV emission. Sunspots would have covered 5 to 30% of the surface. The rotation rate was gradually slowed by magnetic braking, as the Sun's magnetic field interacted with the outflowing solar wind. A vestige of this rapid primordial rotation still survives at the Sun's core, which rotates at a rate of once per week, 4 times the mean surface rotation rate. The Sun consists mainly of the elements hydrogen and helium. At this time in the Sun's life, they account for 74.9% and 23.8%, respectively, of the mass of the Sun in the photosphere. All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen roughly 1% of the Sun's mass, carbon 0.3%, neon 0.2%, and iron 0.2% being the most abundant. The Sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally, it would have been about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. The hydrogen and most of the helium in the Sun would have been produced by Big Bang nucleosynthesis in the first 20 minutes of the universe, and the heavier elements were produced by previous generations of stars before the Sun was formed, and spread into the interstellar medium during the final stages of stellar life, and by events such as supernovae. Since the Sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the Sun has gradually changed. The proportion of helium within the core has increased from about 24% to about 60% due to fusion, and some of the helium and heavy elements have settled from the photosphere toward the center of the Sun because of gravity. The proportions of heavier elements are unchanged. Heat is transferred outward from the Sun's core by radiation rather than by convection. See radiative zone below. So the fusion products are not lifted outward by heat. They remain in the core. 56 and gradually an inner core of helium has begun to form that cannot be fused because presently the Sun's core is not hot or dense enough to fuse helium. In the current photosphere, the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase before nuclear fusion in the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years this gradual buildup will eventually cause the Sun to exit the main sequence and become a red giant. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. Typically, the solar heavy element abundance is described above are measured both by using spectroscopy of the Sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostellar Sun and are thus not affected by the settling of heavy elements. The two methods generally agree well.